Hi everyone. In this video, I am going to discuss the module 14 of our ITN course, which is the transport layer. Transport layer is the second layer of the TCP IP model. It exists between the application layer and network layer. So it stays on top of network layer, getting the services from the network layer while providing the services to the application layer. What it does is it actually builds on the services of the network layer to provide data transfer between process on the source machine to the process on the destination host. So in this particular module, we discuss about these things of the transport layer. If you see here, we first discuss about how does the transport layer does the transportation of data, and we also discuss about the two primary protocols that we use, which is the transmission control protocol TCP and the user datagram protocol UDP. And then we also discuss about the port numbers, how they are used to distinguish between different processes, and how does the TCP communication process takes place, how does it provide the reliability, how does it provide the flow control, and finally we also discuss about the communication process taken by or done by the UDP. So what we are going to primarily discuss about what is the main differences between these TCP and UDP protocols, and which types of process or which kind of applications use these two protocols. So first let us talk about transportation of data. As I told you earlier, transport layer is responsible for logical communication between the applications running on different hosts. The link between the application layer and the lower layers that is responsible for the network transmission. Here, transport layer stays in between your internet layer and the application layer. What it does is these are the main core things that or if you can, if somebody asks you what is the main purpose of a transport layer, these are the following responsibilities. It actually tracks individual conversation. It segments data at the sender side, and then it reassembles the data at the receiver side. This is done actually when the data is larger than the acceptable limit. It obviously adds the header information once again based on the protocol that you have chosen. If you have taken TCP protocol, you add the TCP header, and if you have chosen UDP protocol, then UDP header will be added. So it also identifies, separates, and manages multiple conversations, and it uses the segmentation and multiplexing to enable these different communications happening on the same network. So these are the primary responsibilities of your transport layer. So what are the two transport protocols? So we have studied earlier in the network layer video that IP is a connectionless protocol. It is just a best effort service. It is an unreliable protocol. It does not give you guaranteed transmission. It does not talk about acknowledgements. So we have to build a particular layer which provides all these things to make network reliable. Unless until the communication is reliable, people don't use networks. So on top of this unreliable IP or the network layer, we need to build something which is your transport layer. So there are two primary transport protocols, which are TCP and UDP. So these transport layer protocols specify how to transfer messages between hosts, and they are actually responsible for managing the reliability requirements of a conversation. Once again, based on the requirements itself, either one of these two protocols can be chosen. If your transmission requires reliability, obviously you go with TCP, which is connection oriented protocol. If reliability is not required but prompt delivery is required, then you better off going with UDP protocol, which is a connectionless protocol. We'll be studying more about these two protocols and what type of different applications we use them, what are the different factors that we need to take into consideration. We'll study them in this video. So let's do a quick comparison between these two protocols. So the first one is TCP. TCP stands for Transmission Control Protocol. The basic operations of TCP is it numbers and tracks the data segments transferred or transmitted to a specific host from a specific applications. So it creates a connection, and then it keeps it provides the sequence numbers, and it keeps track of the sequence number. What is the number of which packets are going, which packets are being delivered, all those kind of things. Second one is it acknowledges the receiver data. Once the receiver receives the data that is being sent and there are no errors found, it sends an acknowledgement, positive acknowledgement. Those are there in TCP, and it retransmits any acknowledged data after a certain amount of time. And if we send something to the receiver, and if the receiver does not send you an acknowledgement, it automatically infers that there is some problem with the delivery, and it retransmits the data again. We'll be looking some examples towards the end of this particular module. and sequence data that might arrive in the wrong order. Also, this is called as in order delivery. If the sender is going to transmit the packets in the order of 1, 2, 3, 4, 5 at the receiver, these packets should be delivered to the upper layers in the same order, 1, 2, 3, 4, 5 only. This is called as in order delivery, and TCP also provides this in order delivery and send data at an efficient rate that is acceptable by the receiver. In other terms, we call this as flow control. So flow control is the way of saying that you send the data only at an acceptable rate of the receiver. And if the receiver says, okay, I can only take 10 packets per second, then you only send 10 packets per second. That is called as flow control. So coming to the UDP, UDP stands for User Datagram Protocol. It is a connectionless protocol. It doesn't create any connections. It is also very much similar to IP. It is known as the best effort delivery protocol because there is no acknowledgement of there is no acknowledgement provided by the receiver for any data, and it does not require any connection setup. It is if you want to put it in another way, TCP takes time to transmit the data, whereas UDP does not take any time because there is always a delay involved with the setting up of connections. The same thing does not happen in UDP. I brought some other small diagrams which I found on the internet to give you a better idea regarding the comparison of TCP and UDP. If you see here in this particular thing here, you can say TCP is connection oriented, UDP is connectionless, TCP is state memory because it has to keep in mind which sequence number of packets are being delivered, which are not yet acknowledged. All those things have to be kept. So that is called as stateful, or it is a state memory. It is stateless. TCP works in byte stream mode. UDP is once again you send just some datagrams. UDP once again ordered data delivery. UDP there is no guarantee for this in order delivery. TCP is reliable. UDP is lossy. Error free. Error packets are discarded. The TCP involves a three-way handshake for communication establishment. That is, connection establishment takes place through three-way handshake protocol. We'll be studying about this three-way handshake protocol later. UDP, there is no such thing. TCP also does provide you flow control mechanism, and it makes sure that the receivers, the data rate is actually at an acceptable rate by the receiver. There is no flow control in UDP. TCP is relatively slow simply because you need time to establish this connection, where UDP is relatively fast. TCP supports point-to-point. UDP does support multicasting, and TCP is secure with SSL/TLS, and UDP security is got from DTLS. So there are other two things, and these are the different applications which we will be studying later on a little bit. What type of applications we need the UDP for, and what type of applications prefer TCP as their protocol. So let's start with the TCP protocol, which is transmission control protocol, and what it does. As I told you, it's a connection oriented protocol. These are the key features of a TCP protocol. The first thing is it establishes a session. It is a connection oriented protocol that negotiates and establishes a permanent connection or a session between source and destination devices prior to forwarding any traffic. Simply put, if you are going to take a mobile phone and you are going to call some of your friends, the first thing you need to do is you need to set up a communication first, or establish a connection first. Only then communication can take place. The other mobile whom you are calling, it must be on the connection must be established, a circuit shall be established, and only after everything done, then only you can start talking. So TCP is connection oriented. Remember that before sending any data, you have to establish a connection. Only after successful establishment of a connection, communication can take place. Second thing is it ensures reliable delivery. Once again, reliability comes from error handling. So if you are sending some packets to the receiver, you need to make sure that all these packets are received by the receiver without any errors. We will see what type we use. Actually, internet checksum to make sure that this does not have errors are being identified at the receiver side. And also in order delivery, it provides same order delivery. Networks might have multiple routes possible between the same source and destination. Doesn't matter. It sometimes happen that these different destinations might have different speeds or different data rates supported. So the packets might come out of order at the receiver. But it is the job of the receiver's TCP to make sure that these packets are delivered to the application layer in the same order as they are transmitted from your sender's application layer. So in order delivery is very important. And last thing is supports flow control. I just told you about flow control. Flow control, we have to make sure that the sending application is transmitting data only at a rate acceptable by the receiver. It simply cannot say, I want to send so much of data, I can send whatever I want. Nope. Only when the receiver says so, the sender can send the data. We will be studying about this flow control of TCP also. Next thing is the TCP header. Once again, if you see here, it's a stateful protocol, which means it keeps track of the state of the communication session. TCP records which information it has sent and which information is acknowledged, and for which packets the acknowledgements are yet to be received. All that information has to be maintained. If you see, this is the header that you can see. And for any transport protocol, the two main portions of the header are your source port address and the destination port address. Because ports are used to identify the endpoints of the communication in the source machines, simply, or in other words, saying that on your system, you might have multiple processes running at the same time. In order to identify for which process should this data be delivered, we need to have each one of these application processes do attach themselves to a port number, and based on these port numbers, the data then can be delivered successfully to the intended recipient's process. So this is what we see in the header part. And if we start, source port address and destination port address identifies the two endpoints of your communication, and then followed by the sequence number, which is once again the sequence number identifies, it is 32 bits in number. Also remember that in TCP, each and every byte is numbered. Each and every byte is numbered. So here the sequence number identifies the number of the first byte of your data field. You might have 1000 bytes or 5000 bytes or 10,000 bytes, but the sequence number of the first byte in your data packet will be placed here. This acknowledgement number is the number that the receiver is going to expect from the sender back. So in other words, if I'm sending packet number 1 to the receiver has received it. So it is going to send an acknowledgement number back as 2, because it is expecting the next packet number 2 from the sender. Okay. So the acknowledgement number corresponds to the next packet that the receiver is expecting from the sender. Once again, it is the 32 bits in size, and then followed by header length, which is 4 bits in size. Because you might have options in this. The TCP header the fixed header size is 20 bytes. If you see here, 32, 1, 2, 3, 4, 5. So 532 is 160, 20 bytes it is fixed, and you can add options and padding also, which can be increased for 40 bytes more. So this header length is going to tell the receiver what is the length of this header. In 4 bits it is represented. And then there are 6 reserved bits, which are for future usage. Right now, this reserved field is reduced to 4 bits only. There are 2 other flags which are added, which are going to use for congestion control. The flags that are added are ECE, explicit congestion notification, and echo, ECH, echo notification. So those 2 flags are added later on to support TCP's congestion control policies. The remaining flags are here. One of it is called as urgent pointer. Once again, remember that a flag is a bit. It is either 1 or 0. That is, it is yes or no. If the bit is set, that is, if there is 1 placed here, that means this particular flag has got some significance. In other words, when you are first sending data, there will be no acknowledgement being sent to the receiver. So in that case, what I do is I place in this acknowledgement flag a 0 bit here. When I place a 0 bit here in this particular acknowledgement field, automatically the receiver will know that this acknowledgement number is invalid. And if I am sending a valid acknowledgement number, I will place a 1 in this ACK field. So automatically when the receiver sees a 1 here in this ACK flag, it knows that this acknowledgement number is valid, and it will take that number into consideration. Similarly, push data, PSH stands for push data, RST stands for resetting of connection, SYN stands for synchronization, and FIN stands for finish. So each and every one of these control fields do have a significance. When you are going to try to establish a connection, I told about there is a 3-way handshake protocol that usually TCP employs. For that connection establishment, we use these control flags. So when a sender tries to establish a connection with the receiver, it sends a packet with SYN bit as 1. That means it is requesting synchronization. SYN is equal to 1. When the receiver receives this and it looks at this particular bit set as 1, it knows that the sender is trying to establish a connection with it. Similarly, if you want to close the connection down, you place a 1 in the FIN bit. That means that when the receiver receives a packet with FIN is equal to 1 or FIN bit 1, it knows that the sender is going to terminate the connection, or the sender is requesting to terminate the connection. This is called as the window size, which is 16 bits. This corresponds to the flow control that I just told you. This is going to tell how much of data can the sender send to the receiver. So this window size is filled up by the receiver. It says that, fine, I have so much of space left. You can still send me so many number of bytes. This checksum is used for error control. It is used for error checking. This checksum algorithm we use is the normal internet checksum algorithm. It is an only error detection algorithm. It will only tell you whether an error has happened or not. It does not do error correction. And then something called here is called as urgent pointer. So if you are setting up this urgent flag as 1, it will tell you that this urgent pointer has value, which is valid. If the urgent flag is set to 0, it means that the urgent pointer value is invalid. If it is valid, it will tell you where the data that is to be immediately processed is present. It will point to the byte number where the urgent data is present. This is your TCP header, which is actually added to all the data that is passing through the transport layer and which uses TCP as a protocol. Similarly, we have another header for UDP also. We will discuss that. So these are your fields. I just told you: source port, destination port, sequence number, acknowledgement number, header length, reserved field. As I told you recently that 6-bit field is no more. It's only 4-bit reserved field. There are it says in our content that it is a 6-bit control field, but now it's an 8-bit control field. The two other flags that are added are your ECN, explicit congestion notification, and echo, ECH. Then we have the window size field, then followed by the checksum field and the urgent pointer field. Okay, so let's go to the UDP overview also. What it does, what are the main features, how does it work? UDP features are pretty straightforward because it is connectionless protocol. It doesn't do much. Here data is reconstructed in the order that it is received, that any segments which are lost are not resent. There is, because there is no acknowledgement part here. There is no session establishment. You need not wait. You simply take the data, put it out. You are least bothered about connection establishment. You are not required to. And also the sender is not informed regarding any flow control mechanisms or anything of that sort is not present in the UDP. So this is the UDP header. It's pretty simple when you compare with the TCP header. Once again, the two important fields that we have here are your source port and destination port. And then comes the length field. The length field actually tells you what is the size of this UDP datagram. Usually the packets which are done with UDP are called as datagrams. The name has been analogously brought from the word telegram. You might ask me when you say, sir, you said UDP does not do any error control, but why the checksum field is present here? The checksum field is optional. It's not mandatory. For those applications which might require error control, they can do an optional checksum and place it in this particular field. The size of your UDP header is only 8 bytes, which is 64 bits. Once again, you see those 8 bytes are divided into 4 portions there. Port numbers, both the port number, source port, destination port number, followed by the length of the datagram, and then an optional checksum, which will help for error control. So this is not mandatory. Please remember that. Okay. And what are the applications that use UDP? When you're saying UDP doesn't do error control, it doesn't do flow control, it doesn't do in order delivery, it doesn't establish a connection, it does not send any acknowledgements, then you can ask me, why do we bother about UDP? Why should we study about this UDP? The main reason why we use UDP is because it is very fast. Fast in the sense, TCP is a very complex protocol. TCP, because it being a connection oriented protocol and it provides all the different reliable services that you can think of, it's very complex. It takes a little bit of time for the connection establishment to be happening, and only after that communication can take place. But not all the applications require reliable delivery. Some of them require prompt delivery. So for those applications where reliability is not a big issue, but prompt delivery of the data is an issue, those applications use UDP. Some of the common applications that use UDP are these live video streams, multimedia applications. If you are streaming a song, it doesn't matter if you are losing some data for 10 microseconds or 20 microseconds, it doesn't make a big deal. But for that, if you are going to stop the song, stop the streaming of the song and replay it, it is going to create an irritation to the user. So in those applications where live video, or if you're streaming or you're watching some game online, all those things use UDP itself, because there the application can tolerate data loss, but it cannot tolerate delays. Delays are not acceptable. Okay, and some of the applications are just request reply service, which are like your DHCP and DNS, domain name system, and dynamic host configuration protocol, where they are just a client sends a request and the server sends a response. For simple request and reply services, once again establishing a connection takes too much of time. It is unnecessary usage of unnecessary utilization of the resources. So in those applications which only request and reply service is used, once again UDP is a very good candidate to be used. And also that handle some of the applications like SNMP and TFTP, Trivial File Transfer Protocol, Simple Network Management Protocol, SNMP, where they actually handle reliability themselves. For all those applications also, UDP is the best protocol to be used in your transport layer. Remember that UDP is connectionless. It does not guarantee the delivery of data. It does not give you any acknowledgements. It does not guarantee in-order delivery of service. What it does is it simply sends the data out at a faster rate. The delay that is there with the TCP with connection establishment and all the other reliability features is not present in UDP. Okay, so let us move on and let us talk about port numbers. What are these port numbers? Why do we need them and what role do they play? So usually both TCP and UDP transport layer protocols use the port numbers. I told you there might be multiple applications that are running on the system at the same time. In order to differentiate between these applications, in order to identify which applications or which applications are running, or if the data is being delivered, to which applications should this data be delivered, for all those things we need port numbers. The source port number is associated with the originating application on the local host, whereas the destination port number is associated with the destination application. So if a client in this diagram, if you see here, if a client is sending something to the server, the client's port number is 1025 and it is sending to the server's port number is 80. On this client PC, you might have multiple applications that are working, but this particular application which is being sent, which is sending something to server where it's a web page, where it is requesting a connection through HTTP via port number 80, you can identify. If there is a response coming back from the server, that response will be given to this port number only. Okay, a server can offer more than one service simultaneously. So a server can do a lot of services. So each one of the service will be issued one port number. So you can actually uniquely identify the services provided by the server using the port numbers. Usually the same port number will not be attached to two different services. Okay, so the source, as I told you, when you're sending the data out, these two are your MAC addresses, next followed by your IP addresses, and then followed by your port addresses. You know that. So application data, then we attach the transport layer header where we add the source port, destination port, and then we have the network layer header which tells you which IP address this is, source IP and destination IP, and then followed by the MAC addresses which is used by your data link layer. So this is how usually it is being sent. And please remember this particular term, something called as a socket. A socket is nothing but the combination of your IP address and your port number. So both the IP address, which is 32 bits in length, and your port numbers, which is 16 bits in length, both of them combined form your socket. Usually they say that socket is the end point of communication. So to uniquely identify which is your destination machine and also which process has requested this data on the destination machine, we use a combination of IP address which identifies the machine and the port number which identifies the application. So both of them put together is called as a socket. Okay, so sockets enable multiple processes running on a client to distinguish themselves from each other and multiple connections to a server process to be distinguished from each other. So this is how it usually happens. And let's talk about the different port numbers that are available. How do you identify which port number belongs to which service? Okay, so this is the table which gives you an idea about how the port numbers that we use regularly are grouped. Now, if you look at this particular grouping, port numbers from 0 to 1023 are called as well-known ports. These are actually reserved for the most popular services that we use on a regular basis. I'll show you a common list of well-known or mostly used list of these well-known ports. And port numbers from 1024 to 49151 are called as registered ports. These ports are actually assigned by IANA to a requesting entity. These are specific to be used some with some process or applications, whereas the last one or the last range or the last group of these port numbers called as private or dynamic ports, which are 49152 to 65535. These are also called as ephemeral ports. These ports are actually assigned by your operating system whenever a connection to a service is initiated. So when you're initiating these, usually you get a port number out of this particular range. This dynamic port or these dynamic ports are then used to identify the client application during the communication. When the reply comes back, the reply or that particular communication will be done to this particular port number, to which is being assigned by your operating system. Okay, so this, as I told you, this is the list of some of the port numbers that are usually taken out from your range of the first range, well-known port numbers. If you see the port number, the FTP protocol uses both port numbers 2021, and the protocol they use is TCP. Secure Shell SSH uses 22, once again uses TCP protocol. Telnet 23, SMTP uses 25, domain name system uses 53, and it can make use of UDP or TCP protocols. DHCP 67, DHCP client 68, TFTP trivial file transfer protocol, it uses UDP and the port number is 69. Most common one, HTTP, any client, any browser request you send, HTTP goes to port number 80. POP3, Post Office Protocol version 3, 110. IMAP, once again, it uses TCP. These two protocols, POP and IMAP, are used for email, which we shall cover in the next module. They use 110, 143, and they use TCP as the transport layer protocol. SNMP uses UDP. The port number assigned is 161. And secure HTTP uses 443, and it uses TCP protocol again. So this is how, and there is also one other thing about these port numbers. A network administrator must always know what services are running based on the port numbers that are available. You have to make sure that there are no unauthorized TCP connections that are running on your system. To do that, to verify whether what type of connections are being done to which what is happening with these port numbers, you have a command called as netstat command. Netstat command is the shortcut of network statistics. This command is actually going to give you information about the status of the network and also the ports that are attached. It displays various types of information based on the command line option that you select. There are many options that are there with netstat. So please Google netstat command, and you can actually see many screenshots of how it is being displayed, what type of information it is being displayed there. Usually it tells you whether the port number is there or not. It gives you all that kind of information. You see, an option can be used to display IP addresses and port numbers in their numerical form. So you can type that as well. So let us go to the TCP communication process, how it is done, what is going to happen here. Once again, any application process running on a server is configured to use a port number. I told you earlier that one server cannot have two services assigned to the same port. A server can have multiple services running on it at the same time, and each one of these multiple services will be attached to different port numbers. Now, when an active server application is specific port is considered open, that means that it is ready to accept any connections. So it is available to accept data coming through that particular port number, and it can process the data. Any incoming client request which is coming to the correct socket number will be accepted, processed, and if required, it will send a response back. This is the general TCP server process. And let us talk about the TCP connection establishment. I told you TCP is a connection-oriented protocol, and there is something called as a three-way handshake protocol, which will ensure you that the connection establishment is done without any issues. The first thing, check out this diagram. In this diagram, let us assume that A wants to establish a connection with B. So it sends a TCP header with the SYN bit set as 1. Remember, SYN bit flag. A flag is always set to either 1 or 0. Okay. So it will set the SYN bit, SYN flag as 1 and send to the B. So when B receives this, it understands that, okay, A is trying to establish a connection with me. And then if it's okay, if there are no other issues, and if it is ready to accept any connections, it will send a response back. Also, please see that The sequence number is selected by A is 100, and the control flag sent by A will be S1 is equal to 1. Now for this particular request, B is going to send another message which it selects its own sequence number. The sequence number selected by B is 300, and it is also sending an acknowledgement number as 101. The reason for sending 101 is because it has received already a packet with number 100. The next packet which A should be sending is 101. So it is saying to A that I am expecting the next one packet as packet 101 from you, and it will also send the control flags S1 is equal to 1, which indicates A that B is also ready to establish, B is accepting its request, and it will also say that ACK is equal to 1. Now A will check this message. A knows that okay, the packet which I sent 100 is gone through to B successfully. B is also happy to accept my connection, so it has sent us S1 is equal to 1, and it also checks the ACK is equal to 101. Now it sends a third message back acknowledging this S1 bit sent from B. So it is now sending, okay, next one is sequence is equal to 101, ACK is equal to 301. Here, why we sent ACK is equal to 301? Because B has selected the sequence number as 300, and the first message sent from B has the sequence number as 300. The next sequence number which A expects from B is 301. So it is sending it as an acknowledgement. And control flag will be ACK because there is no synchronization has been done. So these three messages which happen one after the another, step 1 to step 3, is called a three-way handshake protocol. This handshake protocol validates that the destination host is available to communicate. Okay, and the exchanges are being done and the session will be established from right on. After the three-way handshake, the actual data communication can start happening. Okay, now what happens if you want to close the session? So how do you do it? Once again, it's just similar to when you're talking on the mobile phone. When you want to disconnect, you'll say, okay, fine, thank you very much, bye. The other person, you also wait for the other person to say that bye. Okay, and then you disconnect. Similar, that is called as a synchronous termination. Sometimes out of anger, you simply switch, cut out the conversations. It is called as asynchronous. Even though the other person is trying to speak or is sending some data to you, if you want to close the connection out, that is called as asynchronous. TCP does a synchronous connection only. Now, for that reason, what it does is it will send a packet with the finish bit as 1. The control flag will be set. That means there is a 1 placed in that control flag. Now, when once again A is sending a finish to B, it receives this finish and say, okay, fine, thank you. And then after sending this, it will also send a FN bit is equal to 1. And for that, A sends an acknowledgement. Now, what happens with these 4 messages is that B knows that A is going to close down the connection, and also it understands that A got no data, nothing else to send to B. Similarly, after this exchange, A also understands that B is okay to close the connection, and B also has got no data to send. So then both A and B does close the connection out. So this is called as a session termination or as a synchronous termination. So usually we don't require these 4 steps because both these things can be sent in the same header. You can send an acknowledgement ACK is equal to 1, and in the same FIN is equal to 1 also. You actually do not require all these 4 steps. But in some cases where B has got data to send, it will not send this FIN message. First, it will send the data, and after the data is being sent, and then it will send the finish bit as 1. Okay. So this is how, if you want to close a session down, this is how it usually happens. Okay. Now, the three-way handshake analysis. What does it do? What are the functions of the three-way handshake? What it does is, TCP is a full duplex protocol. So we discussed in the very earlier videos. So full duplex communication, half duplex communication, simplex communication. Full duplex communication means communication happens in both the directions at all times. Okay. And also it means that each connection represents a 2 one-way communication sessions. Now, what happens with this when you want to establish such a connection using a three-way handshake? It establishes that the destination device is present. So it will then tell you. It also verifies that the destination has an active service and it is accepting the request. So when you send a SYN bit as 1, when the destination responds to that particular message by its own S1 is equal to 1, it means that it is going to accept communication for that particular service on that particular port number. Okay. And the destination is also going to know that, okay, the sender is trying to establish a communication with me with that particular port number and for what type of service. So after the communication is completed, the sessions are closed. So after the three-way handshake, a session is established, and after the session is established, communication starts happening. And after the communication takes place and everything is done, you close the session. That is called as session termination. So the connection and session mechanisms enable the TCP reliability functionality. We told you that TCP is a reliable protocol. So all these are the reliability part of TCP, establishing a session, how do you terminate the sessions, all those things. And we discussed this in the earlier header part itself. I told you that the control fields are called as flags. A flag is just a bit. It is either on or off, just like your switch, on or off. That's all. Okay, either 1 or 0. 1 means it is set, 0 means it is reset. So based on these control fields, I can actually establish connections and I can exchange a lot of information between the sender and the receiving entities. Okay, I already told you. So we don't want to talk about again. So let's talk about the reliability and the flow control part of the TCP sessions. Or how does TCP handle that? So unlike TCP, we discussed earlier, unlike UDP, TCP resends the dropped packets and numbers packets to indicate their proper order before delivery. Now, just using common sense, if AO is going to send packets to B, when I'm sending 5 packets, I usually, if I number them from 1, 2, 3, 4, 5, and if the receiver receives 1, 2, and then 5, it automatically, the receiver knows that it has missed 2 packets. And it can send the information that to the sender saying that I did not receive the packets number 3 and 4, maybe they are lost during transit. So for those reasons, in the TCP does assign sequence numbers to all the data packets that are going out. So also TCP maintains the flow of packets to achieve that flow control and the devices do not become overloaded. It has to make sure that the network is not overloaded and also the receiver gets inundated. It should not get inundated with the too much traffic being sent by the sender. As I told you, there are no network is 100% error free. Sometimes the packets are being lost. Sometimes the packets might arrive out of order. All of these issues must be taken care of by TCP. Once again, the whatever data is being received by the receiver, if you see in this particular diagram also, the sender has sent segment 1, 2, 3, 4, 5, 6. They are taken. They might take different routes as indicated over here. They might take different routes, and at the receiver they have received in the order 1, 2, 6, 5, 4, 3. But it is up to the TCP to make sure that these datagrams or these segments are reordered to the according to the sender. So 1, 2, 3, 4, 5, 6, and once again they are reordered into the correct order delivery, and then only they are passed to the application layer. Under no circumstances TCP allows these segments to be passed on to the application layer out of order. Okay, this is one of the reliability feature. As I told you, sequence numbers are assigned in the header of each packet to achieve this goal. I have told you about the sequence number. It's a 32-bit in length. And what do you talk about or how do you handle data loss and retransmission? I told you earlier itself, doesn't matter how good a network is, always data loss occurs for whatever reason it might be. So TCP also should be having some mechanisms to handle this data loss and also how to retransmit. Now, in this particular example, so the sender keeps on sending data segment 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Unfortunately, segment 3 and segment 4 are lost. Okay. So once it has received the segment 1, 2, and it did not receive the 3 and 4, what the receiver will say is it will send an acknowledgement 3. It will send an acknowledgement 3. So once it has sent the acknowledgement 3, the sender will understand that there is something happened and it is still expecting the third segment. So it will resend from here onwards. So segment 3, 4, 5, 6, 7, 8, 9, 10. Once again, so the sender is going to send all these segments again because the receiver did not receive these two. How did the sender know that the receiver did not receive these two segments? It knows that because the sender did not send acknowledgement 11 in the here. It sent only acknowledgement 3. That means that the receiver is expecting the third segment. So all of these are sent again and acknowledgement 11 is now given here. And now after seeing this acknowledgement 11, the sender understands that all the data packets from 1 till 10 are received in the correct order by your receiver. So it creates some duplicate segments also. There are ways around it, as I told you. The sequence number identifies the first byte of data in the segment being transmitted, and TCP uses the acknowledgement number sent back to the source to indicate the next byte that the receiver expects to receive. The name given to such kind of acknowledgement is called as expectational acknowledgement. So here, acknowledgement number is the next byte that the receiver is expecting from the sender. Okay, so this is how it is done. It is called as exception. Now, as you see in the earlier example, that there are too many duplicate segments that are being sent. In order to overcome this, duplicate segments once again make use of a lot of network resources, which is unnecessary wastage. So in order to overcome that, we have a special feature, something called as selective acknowledgements, SACK. This is not by defaultly set in the TCP, and only if both the hosts support it and they do this during connection establishment only in the options field, then SACK can be used. Same example if you see here, once you send all these data packets to the receiver, in order to send ACK3, now the receiver is also sending something called as selective acknowledgements 5 to 10. That means it is saying that, okay, fine, I received 1, 2, I did not receive 3, and I also received from 5, 6, 7, 8, 9, 10. The sender understands that, okay, so what it is missing? 3 is missing. There is no 4 here, so 4 is missing, but 5 to 10 are already there. So instead of sending all these segments again, what the sender is now going to do is, it is going to only send those 2 segments which are lost, in addition to any other new segments it might have. So once segment 12 comes in, the receiver is going to send acknowledgement 13. So once you have this acknowledgement 13, which is a cumulative acknowledgement, automatically the sender understands that, okay, segment number 1 till segment number 12 are received by the receiver. They have gone correctly. So this is how it is being done. This is called as a selective acknowledgement. It is actually negotiated during the three-way handshake protocol. These are added in your options field of your header. And to understand how much time does the sender has to wait for the receiver to send an acknowledgement back, we use the concept of timers. We use something called as a retransmission timer, which you calculate based on the round trip time or the average of the round trip time. So based on that, we keep a timer, and you simply can't wait for an acknowledgement. So there might be some issues where the acknowledgement might not happen, where the receiver's acknowledgement is gone. How much time does the sender has to wait? He can't simply keep waiting for infinite amount of time waiting for the acknowledgement to be back. So in those cases, we use this retransmission timer, and even though the data might have been received correctly at the receiver, but still, because the acknowledgement is lost, the sender has to retransmit these things. So in those cases, we use the timers to make sure that the sender does not go on in an infinite wait. Okay. So this is once again the flow control part of TCP, which is a very important one. We have seen a field in the TCP header, which said window size. I told you at that point that window size is nothing but the amount of data that the receiver is going to tell the sender that it can accept. Simple and straight. The receiver, if it is going to tell me, okay, this is what I can accept, only that data only the sender can send. Check out this example. So usually we have another term, something called as maximum segment size. I'll tell you how that maximum segment size is calculated. It is usually 1460. So during the three-way handshake, it is said that the window size is 10,000 bytes. That means the receiver's buffer is 10,000 bytes, and the sender can only send in bursts of 1460. That one burst can only have 1460 bytes. So sequence number 1, it sent 1460 bytes. The receiver received them. Now, after that, once again, what it does is it has sent the second one also, second segment also. In the second segment, the sequence number will be the first byte. Which is the first byte? We have sent until 1460. In the second segment, the first byte will be 1461. So the sequence number is 1461 to 2920. Let us assume that these two segments are actually received at the destination without any errors. So now the destination is going to send an acknowledgement back. It is going to send, because it is expecting the next byte. It says acknowledgement is equal to 2921, and also assume that if these two segments are delivered to the application layer, the buffer is still empty. What is the buffer size? 10,000, or the window size is 10,000. And it is saying, okay, fine, you can still send me 10,000 bytes. Then the sender sends another segment. It says, see, the sequence number is 2921, and it sends 4380. And this is also delivered to the application layer, and the receiver sends another acknowledgement saying that the next byte I'm expecting is 4381 and still my window size is 10,000 bytes. In some cases where if the receiving entity is unable to deliver these bytes to the application layer, the window size will be reduced. That means I cannot send the window size is 10,000 bytes anymore, because if I have already 2020 bytes, I can't send this, right? I can only send the window size is 7080 bytes, 7080 bytes. Okay. Then because these are still in my buffer, so this window size corresponds to the number of bytes that the receiver can accept from the sender. That's all, nothing more than that. So why do we bother? We want to make sure that the sender does not send the data at any price at a rate which it wants. It needs to send the data only at an acceptable rate of the receiver. This is how you do this. For this reason, we have incorporated a 16-bit field called the window size in the TCP header. This is how it happens. This is how TCP maintains flow control using the window size field and your acknowledgement field. And as I told you, the MSS is called as maximum segment size. That means at one stretch, at one for sending one set, what is the maximum number of amount of data? This 1460 is calculated using the from the sizes of the headers. So usually you know that the Ethernet's maximum MTU or the maximum transmission unit is 1500 bytes. So out of this 1500 bytes, if you remove the 40, so what is this 40? 20 bytes from the IPv4 header and 20 bytes for the TCP header, which you are left over with 1460 bytes. That is the reason usually the common value for one MSS in networks is 1460 bytes. This is when you're using IPv4. Okay. So how do you talk about congestion avoidance? What is do? Once again, congestion avoidance, there are many algorithms at work. TCP employs something called as slow start, fast retransmit, fast recovery. These algorithms are actually being used by TCP to do congestion control. Usually when there is a congestion, packets are being dropped by the network. So whatever packets are being dropped, TCP will retransmit. But the problem here is if you don't control this retransmission, all these retransmissions are also going to increase the traffic on the network. So creating even a bigger problem. So that is the reason, in order to make sure that this does not happen, or the TCP blindly can't simply keep on retransmitting when a congestion happens. We have many congestion handling algorithms. We have timers. We have I told you, slow start protocols, fast retransmit protocol, AIMD algorithm, additive increase, multiplicative decrease algorithms. All these algorithms are used by the TCP to provide congestion control. So congestion control is also an integral feature of TCP protocol. We have come to the last part of your this particular module called as UDP communication. As I told you, UDP is straightforward, nothing. It doesn't give you anything. It actually delivers the datagrams as they are received from the network. It doesn't reorder them or doesn't do anything. Because reorder of delivery, establishment of communication, all of this include time delays. And UDP is best suited for those applications which are delay sensitive. So for that reason, it does not establish a connection, and it provides very low overhead data. I have seen the header of UDP. It has only 64 bytes. Okay, so it is a very small. As I told you, it does not track sequence number, no reordering of the datagrams. It does not do any acknowledgements. It simply forwards the data onto the network. Prompt delivery. UDP is used by the applications where prompt delivery makes sense rather than reliable delivery. You must have seen based on the protocols that use this UDP transmission. So these are the UDP servers and process and requests. Once again, what types are used? These are most of the UDP based server applications are assigned the well-known or the registered port numbers. So based on the port numbers, the client can send the request, and if the server sends a reply back based on this destination port number, that data will be delivered back to the client application process. This is how it does. And once again, it actually does the dynamically. I will told you about the port numbers. The client actually selects dynamically one of the port numbers, and then it knows what the port number for the source particular service. It creates a UDP packet. It puts all this information into the header, and then it sends out. If you see here, DNS, radius, all these things. Okay, so let us come to the final part of the UDP, this particular module, transport layer. What we studied until now, we studied that there are two main protocols in transport layer, TCP and UDP, and it is the transport layer is the link between the application layer and the lower layers which are responsible for the network transmission. TCP is a connection oriented protocol. It establishes the sessions, it ensures reliability, provides in order delivery, and it also provides flow control as well as congestion control also. UDP is a pretty basic protocol. It is connectionless, and both the TCP and UDP protocols make use of port numbers to manage multiple simultaneous conversations. Each and every process or application process that is running on a server is configured to use a port number. Generally, these port numbers are automatically assigned or configured manually by a system administrator. You have seen the other groups of port numbers also. And the common value for one MSS or maximum segment size is 1460 bytes. And once again, if we talk about, there are many, TCP also employs many congestion control handling mechanisms, including the slow start mechanism, fast retransmit, fast recovery. All those things are being done by TCP to provide congestion control. Each and every data byte in TCP has a sequence number attached to it. These sequence numbers are used to provide the reliability service, to provide in order delivery, to provide error free delivery, to identify the packet loss, all those kind of things. So I hopefully most all of you guys have understood the importance of transport protocol. The main objective here is how do you identify which protocol is to be used for what type of application process. For applications which require or which are not bothered about reliability, you are very much better off using UDP because of its prompt delivery. Okay, so thank you very much. And in the next module, we shall discuss about the application layer. Thank you.